Hi everybody, welcome back to Linear Algebra with me. We're going to talk about vectors and vector equations today. And what we're going to build up to, so our big idea for today is that we want to find out if a system of linear equations has a solution, just like last time, but we're going to ask this question in a really different way. You're probably not even going to see it until I tell you. What we're going to need to do that, though, is we're going to need to review vectors first. Remember vectors from Calc 3 for me real quick. You might remember that we could have a vector v, and we probably wrote it like this, and that would be a vector in R2. Or you had a vector w, and it looked maybe like this, and that would be a vector in R3. These are called row vectors, and we are less interested in row vectors. We are more interested in column vectors. So column vectors equivalently would be v equals, and we're going to go up and down. So now our entries are exactly the same. They're just up and down instead of left and right. There we go. And then I've got a fancy definition for you for a column vector in Rn. It has the form starting up at the top and moving down to the bottom instead of left and right, where all of the entries are real. They're just normal numbers. Okay, and we're going to review some properties about vectors. Notice that A and B are the same length. We can define vector addition, but only if they are the same length, like this. You just add the first entry with the first entry, second entry with the second entry, all the way down to the very last entry. And then I have some cool visualizations for you guys. Here in Mathematica, I've made it so that you can evaluate the cells yourself. I wrote some instructions, so it says click on the section of code below. It's called a cell, so that would be the code down here. And you can press Shift Enter to evaluate it, or you can come over and you can click Evaluate Cell over here on the, if you right click it. All right, and so that gives us this really cool looking plot. So what we've got here is a blue vector, v, and the entries are going to be a, b. And we can change values of a, b here. So that would change vector v. And vector w is entries x, y, and you can change them here. And then the green arrow is going to be the sum of the two of them together. And then note you can click on the little plus sign if you go down to the next bit of instructions, so the plus sign here, and you can see what the values of a and b actually are. So if we wanted to know what, if we had vector 5 and -5 is v, so 5 and -5, and then we wanted to add, we'll say, we'll go with 4 and +3. What would that look like? Here you go. Here's your 5, -5 vector, and then plus 3, -4. And then you can notice that if you play with the first component of one vector, the result just moves horizontal because it's only expecting the first component. And if you move the second component, that only moves it up and down because you're only affecting the second component. Okay, but that's our visualization for vector addition. And then we have scalar multiplication. So that's where you take a scalar like c and you multiply your vector. And you do that component-wise as well. Except you take the same c and you multiply each component. And then I've got a visualization for that as well. If we come here to Mathematica again, so the next piece of code says click on the cell below, hit Shift Enter, or right click and hit Evaluate. And now we can see that for the blue vector, which is v, and we have it as being 4, 2. We have vector w, which is red, and w this time is just a constant multiple of v, where it's been multiplied by c. And we can click the plus sign so we can see what c is. And you can see how the red would compare to blue. It stretches, or it goes in the opposite direction when it's negative. Okay, so now we get to move on to some algebraic properties real quick. For instance, it doesn't matter what order you add your vectors in. You can do a plus b or b plus a. Doesn't matter. There's the transitive property, and I'm not really going to read through all of these, but this is just a refresher for you. Quick note, the zero vector is just equal to a vector where zeros are all the entries, and we want to have n many of them. So same size as a. You can verify any of these component-wise, by which I mean if I wanted to verify the very first one, a plus b is equal to b plus a. I know what that looks like because we just did vector addition on the previous page. And then we know that 3 plus 4 is the same thing as 4 plus 3. And so we're allowed to switch b1 and a1. In fact, we can switch it for each of these entries. And then we can undo the vector addition, split it back apart, and now the vectors will be backwards. So that's what I mean by you can verify any of these component-wise. Okay, so that was fun. Now we get to get into the real good stuff. So we've got vectors can be written as a linear combination. This should remind you of linear equations from yesterday. You've got your vectors, and all you're going to do is you're going to multiply them by a constant C1, C2, all the way up to CP, depending on how many vectors you have, which is P many in this case. And then you add them all together. That is the only thing you're allowed to do with them. No multiplying V times V, no exponents, same thing as equations, just constants. And then just a quick note, we've got CI can be called a coefficient, or we can call it a weight. It goes by either name. So for our first example, we're going to calculate a linear combination just to get a little bit comfortable with dealing with vectors and stuff. So can we find y if y is equal to 4 times v1, negative 4, plus 7 times v2? I'm going to say yes. All we have to do is distribute that 4 to each component in our first vector. And then same with the 7, we will distribute him to each of component in V2. And then we know how to do vector addition from page 2. So we go through component-wise, 14 minus 12, 49 minus 4, 7 minus 16. Done. This is our y. Okay, so now that we have linear combinations, now we can talk about an important concept called span. So span of our vectors here is denoted just by putting span on the outside of the set right here. And what the span is the collection of all linear combinations of the vectors that we want to look at. So you would put the C1, the C2, and all combinations of the C1s and C2s, those are all going to be in the span. So question, something easy, is the 0 vector in the span of this random set V1, V2, up to VP. I'm like, well, we don't know what they are. That might be a problem, right? Not at all. All you have to do is make all your coefficients 0. Answer, set all CI equal to 0. If all your coefficients are 0, then you're going to get the 0 vector. Done. Okay, so let's look at what the span of some of these is going to look like. So the span of the 0 vector would be all linear combinations of the 0 vector, which is just going to be a constant times the 0 vector. That's still the 0 vector. So that's very unexciting. What about the span for V? This is going to be a little bit interesting. So we've got C1, or maybe just a C, times V. What does that look like, though? You can have anything multiplied by V, or any number. Well, let's go back. We actually know what that looks like. It looks like this. It's that red guy. You can have very big constants. You can have negative constants being multiplied. We need something that incorporates all this information. Well, that would be a line going through the origin, and as long as it incorporates our original blue arrow, it'll have the right slope. So the line through the origin containing V. Yeah. Okay, so what if we look at the span of 2 vectors now? Might seem a little bit more daunting of a task, but I believe in us. So that would look like any combination of C2 and C1 that we can come up with and add them together. So like if C1 is 0, then you get C1 is 0, C2 is 1, then we're going to get just V. If we have C1 is 1 and C2 is 0, then we're going to get just U. And so those are going to be in the span. You're always going to get that just themselves is going to be in the span. But like what else? Like how do we summarize all this information? I have another visualization for you guys. We're going to come down here and we're going to evaluate this cell. And this time I picked specific vectors for V and U. So V is 4, 2, 3, and I said U was 1, 3, negative 1, and then I multiplied them by constants C1 and C2, and we can play with those constants here to see what we're kind of getting. You can see that they're kind of moving like all over the place. But it does seem to have like some sort of pattern-ish. And what I've done here is I've added an extra thing. So this is the same thing, but now I'm added a plane. Look at this. They're staying on that plane. We can move that around some more. See, they are on the plane no matter what you do with the constants. So we know that, let's see, what was it? We know that V is going to be in there. We know U is going to be in there. And we can summarize that information with a plane. You guys know from Calc 3 how to find the equation of a plane if you've been given 2 vectors. So the plane going through the origin and containing U and V. And that's how we would summarize that information. So if we move even bigger than that, maybe we could span the entire set, like the entire space. You could fill up the cube that we just looked at. And like, yeah, if you have the right vectors, we could say that V1 through VP spans Rn if the span is equal to the entire space. And what that actually means more explicitly is we can write any vector in Rn as a linear combination of V1 through VP. Okay, so you might be thinking at this point, like, Gracie, we've gone off the rails. This is not like yesterday at all. How does this relate to linear equation stuff from last time? Really glad you asked. I'm going to redirect us with the question, how can we determine if a vector B is in the span of some vectors? So we've talked about what the span might look like for a couple of cases, but if I handed you a vector, could you tell me if it was in the span? The answer is yes, with a little bit of prompting from me. Let's go off with an actual example. We want to know if this B here is in the span of these three vectors. So let's think about what that means. What are they trying to ask us? They want to know if it's in the span, that means there's a linear combination that's going to be equal to B. So let's write out what a linear combination is going to look like. We want to know if do constants C1, C2, C3 exist such that scoot this a little bit, such that their linear combination is equal to B. So if this is the linear combination, can we find constants so that's going to be equal to B? Well, it might not be obvious first off, but yeah, there is a way to figure it out. I'm going to use some properties of vectors, and I'm going to manipulate this problem for us. So let's substitute what V1 is. That's 1, 0, negative 2, plus C2, negative 4, 3, 8, plus C3, 2, 5, negative 4. And is that going to be equal to 2, 5, negative 4? You're like, Gracie, this isn't much better. Okay, let's try distributing constants. Scalar multiplication, we can do that. So that's going to look like C1, 0, negative 2, plus, negative 2C1, negative 4C2, 3C2, 8C2, plus 2C3, 5C3, minus 4C3 equals 2, 5, negative 4. But I'm not done. We use scalar multiplication. Now let's use some vector addition. Let's add those vectors together. So now it looks like C1 minus 4C2 plus 2C3, 3C2 plus 5C3, negative 2C1 plus 8C2 minus 4C3 on the left, and that has to be equal to the vector 2, 5, 4. I'm like, okay, Gracie, this is like maybe better, I guess. Going to do one more thing. So this top row, if these vectors are equal, their top rows have to be equal. So I'm going to write that information out on the next page. So C1 minus 4C2 plus 2C3 is equal to 3. Same thing goes for the other equations. 3C2 plus 5C3 equals -7. -2C1 plus 8C2 minus 4C3 equals -3. Does this look familiar yet? We're not using x's, but this is a system of linear equations. So if we can solve this, we can find the c's. If we can find the c's right here, can we find the c's such that this is true? If we find the c's, that means that B is in the span, because yes, those c's exist. So let's go ahead and try and find those c's using the techniques that we learned from last time. So first of all, what are we going to do? I hope you're shouting that we're going to do an augmented matrix. I'm going to pretend you are because it makes me happy. So 1, -4, 2, 3. There we go. 3, 5, -7. -2, 8, -4, -3. Okay, so what do we want to do now that we have our augmented matrix? Well, we would like to have like some sort of staircasey zero so that we can have like ones going along our diagonal. So what's standing in our way? This -2. Right now, he's my biggest enemy. I would like to remove him. So let's go after him first. We can do that by modifying row 3. We're going to add 2 times row 1. Rows 1 and 2 don't change, so we copy them down. Okay, so first entry, -2 plus 2, 0. Great. Next entry, 8 minus 8, that's 0. All right, we got that one for free, that's cool. And then we've got -4 plus 4, and then we have -3 plus 6, so 3. What does that mean? Hopefully you're shouting, no solution. Okay, so what does that mean for our problem then? We asked, is B in the span of these V vectors? No, no such C's exist, therefore B is not in the span of V1, V2, V3. Okay. So this problem is really cool because it just related span back to solving systems of linear equations. And I want to make a note right here. Look at this column. That's V1. Right here. What if we look at column 2? Column 2 is V2. Column 3 is V3. And then what about this last one? What's that? That was B. So I showed you like how to do like all this thinking over here. Hopefully you followed it with me. But in the future, you can just skip to the augmented matrix because you know, oh, B being in the span is the same thing as solving this augmented matrix. In fact, I'm going to write it down for you because it is that important. Proving that B is in the span of V1 up to VP is the same thing as solving the augmented matrix where V1, and I'm going to do like these little arrows to kind of show that these vectors are taking up the entire matrix. There we go. So this augmented matrix right here. So all we did today was I introduced some concept called span, which that's going to move on and we're going to do some fantastic things with span. But span is just solving systems of linear equations. All right, that's our takeaway for today. Thank you so much.